And then I don't know.
Give me a little bit. I brought 2 things. I brought 1 jam.
Have you?
I'll get 1.
Yeah, we did. I didn't do it. No.
Plus it's 4 mistakes.
Yeah, I think I did on the iPad. Yeah, apparently I was also thinking of doing it on the iPad.
Okay. Work on it until 4. Then 6 I'm also done.
Welcome back
Let's see how far we
to
get.
You can like draw it on that.
welcome back to our
You know how to
machine
explain
learning
the
systems
ensemble
and hardware. So today is actually our last lecture. I just realized this morning. Before we start, let me just briefly mention several things. So I think I didn't use this. Yeah, before we start, so today this is the main 3 parts we'll cover in today's lecture. So in the first part we will cover distributed training, and in the second part we'll learn the distributed inference. In the last part, I will help you to understand the latest large language model optimization called test time scaling. Before we start, there's several things. The first one is, can everyone see my the submission entry of my module now? I think some students mentioning I didn't specify the deliverables in the system. Now it's okay, right? Okay, yes. So this is the coursework. And the second one is about the screenshots. Some students were asking in the AppStem system. So for screenshot, basically you just need to attach something like showing this slide. It basically contains the submission ID, such that we can also track your submission in our evaluation platform. And you also need to just get the screenshot of like the test, the time cost, and the test cases, the correctness. So this is basically it's not. Will occupy a large space in your report. So we still decide to go to 2 pages. But if you need more, you want more explanation, so just use instead of 11 pt, just use 10 pt to write your report. And again, so we will not evaluate on the quality of the report. So the report is just used to help us to cross-check. You understand all the implementation you have. So the final evaluation is still based on first, correctness, and the second, performance. So this is something I want to mention for our coursework. And this is an updated table. I think I put the same in the 3rd week, but some students still confused about timetable. So today is our last lecture. Actually, we'll cover distributed machine learning system. And so in this Thursday, we will have tutorial for this distributed machine learning system, and we'll we will decide is the paper reading or others. And in 24th of November, we will have industrial lecture. So this is the information of our invited speaker. So his group lead in Samsung AI Center was working on machine learning system and hardware. So I also put the information of the industrial lecture in the section in the AdStan system. I hope everyone can see the information. Like what is the title, what is the information. You can check all this in our AdStan system. So okay, so before we start the distributed machine learning system part, which is the main topic of today's lecture, let's just recap what we have covered in last week. So in past few weeks, we covered this topic called efficient ML, and we know different redundancy actually is existing in different levels of this machine learning algorithm stack. So basically, starting from the most fine granularity, so you have the precision level redundancy. So you apply the quantization. For example, so this is kind of you are trying to exploit the big level redundancy. And you also have one level above. You have different pooling strategy. So this is more like tensor level sparsity of redundancy. You try to, for example, remove the whole channel, or remove, for example, the entire rows in low rank factorization pruning. And further, one level above, you have the operator level redundancy. So this is kind of redundancy you can exploit when you design the operator itself at the beginning. You consider what kind of redundancy it will have. And the last part we introduced is the architecture level redundancy, and we introduced an idea called neural architecture search. So in the neural architecture search, we introduced this reinforcement learning based framework, and we mentioned one of the problems of this neural architecture search is it requires 22,000 GPU hours, which equals to nearly 3 years to train if we train on a single GPU. So the problem proposed by Google when they try to do this neural architecture search is they try to deploy a distributed training system which consists of here 800 GPUs to parallelly train different neural network candidates. And it reduced the training time to 28 days. So in this work, so in today's lecture, we'll then how this distributed machine learning system actually work. So this is a very practical, even very practical problem in industrial setting. For example, if you have a large language model, what I want is how to separate the inference workloads of this large language model to different GPUs. Because when we're talking about large language model, it's like some big model might have 1 trillion parameters. You cannot fit in one single GPU. So either in training and inference, we need this distributed system. So as I mentioned before, this is the main topic we will cover. So the first part, we will introduce the distributed machine learning system for training. So in this part, what we will teach is we will teach you the different types of communication collectives and different types of power reason strategies. And also, in the end, we will introduce an algorithm variant of distributed training, which is called federated learning. So this algorithm actually is proposed to protect your privacy. And in the second part, we will then distributed machine learning system for inference. And I will introduce a very recent research, which is called disaggregated prefill and decoding. And in the last part, so we'll briefly discuss the performance scaling of large language model. So I will teach what is the scaling law of large language model and what a problem now that this scaling has, and what is the current research direction to keep improving the performance when we see this end of scaling law of large language model. Okay, so let's start from this single GPU training example. So this is the simple pipeline we introduced in our first lecture, basically. So if you can see, this single GPU training is actually basically contains an iterative process. So basically, you need to perform this forward pass, right? And you calculate this loss, and you backward pass, and you update all parameters. This is the basic pipeline of a single GPU training, right? So, but there are several limitations. Let's say you have a server. It consists of, let's say, 8 GPUs, and you want to leverage these 8 GPUs to speed up your training. How can you do this? So we need distributed machine learning system. And also, as I mentioned before, this single GPU limits the more. If let's say we only leverage one GPU for training, it actually limits the model size you can train on this single GPU. So there are 2 limitations. The first is the speed limitation. Let's say you have a lot of GPU. You basically want to leverage all this GPU to speed up your training time. And the second is memory consumption. Let's say you have a model where you want to train it to, let's say, billions of parameters, and this single GPU cannot hold all these parameters and activations. So this is the motivation why we need distributed training. So this is the motivation. And in terms of the distributed training, there are 2 key components. The first one is communication. Assuming like you are basically you are trying to use the basic parallelism we introduced in next slide, which is called data parallelism. So how to do this communication is very important because let's say you need to collect all different gradients in different GPUs, and you need to do aggregation gradients. You need to do parameter updates. How you can collect different gradients from different GPUs to do this synchronization. This is first part, very important, communication. And the second is the parallelism. How do you divide your computation among different GPUs? So this is the second part we'll introduce, different parallelism strategy. So let's start from the first part, communication collectives. So I will introduce them one by one. So the first one is called broadcast. So the idea is very simple. Let's assume in here you have multiple GPUs. Like 1, 2, 3, 4. So the basic idea of broadcast is you send the data from the root device. Let's say here, the rack 2 is your root GPU. So you basically just want to send this data to all different devices. So this is broadcast. And the user case of this broadcast is usually, for example, you want to distribute all your parameters to different devices for distributed training. You want to set all the parameters to different GPU. So this is the broadcast. And the second is reduce. So this is the second communication collectives. So the basic idea is to perform reduction on data across different devices. So one of the most simple example is for reduction is you do this accumulation. So let's say I have 4 data copies or 4 chunk of data. They have the same shape. Let's say just very simple, 2 times 2 matrices, and you have this for each device, and they are all holding different data. And what you want to do using this reduce is you want to accumulate them together. For example, in here, you want to accumulate them together in this root device. So you just collect data from different rank to this root rank or root GPU and do this accumulation. So this is the second reduce. And you can also have point-to-point communication, which means you specify, let's say you want to set some data from the first rank to, for example, the third rank. So you basically have this point-to-point communication which specify the explicit destination device and your root device. So this is clear, right? Any question on this? Yeah.
What do you mean by rank?
So rank, you can just, in here, you can just assume this is one GPU. Okay, so this is the first three communication collectives. So remember this, and now we will go dive into more complicated communication collectives. And the second, the first one in this slide is called gather. So basically, this is very needed if, let's say, you have different gradients on different devices, and you want to gather all these different data from different devices in the root or the root GPU. So basically, what you're doing is, let's say you have different chunk of data in rank 1, 0, rank 1, rank 2, rank 3, and you call these communication collectives called together in, for example, the second rank, the second GPU. So basically, you just collect all different data copies across different devices. So this is called gather. And the reverse operation of gather is called scatter. So let's say in one rank, for example, again the same example, in the second GPU, you have 4 chunks of data in here, right? Let's say just assume you have 4 elements. And what you want is in the second GPU, you call these scatter communication collectives, and you basically just send all different pieces of data to different devices. So this is called scatter. Just scatter, yeah. And the last one is called all gather. So the basic idea of all gather is it basically contains 2 phases based on the basic communication collectives we introduced before. So remember now, so in this slide, we introduced 3 communication collectives, and in this slide, we introduced 2 basic communication collectives. And after this point, more complicated communication collectives is basically a different combination of different basic communication collectives. This is clear, right? Yeah. So before I introduce all gather, any issue on these basic communication collectives?
Between reduce and gather.
The difference between reduce and scatter. Okay, so
Gather.
sorry,
Reduce and gather.
reduce and gather. Okay, so reduce is more like you. Okay, let me check. So in here, reduce means you have the, let's say, okay. So maybe I can explain this using the shape of matrices. So in here, for reduce, let's assume for each rank, you have 4 times 4 matrices again. So towards the end, in this root matrix, after this reduce, you will have 2 times 2, the matrix with the shape 2 times 2. However, in this gather, let's assume this 4 gather, assume this data chunk is also 2 times 2. So when you apply this gather, you will have 4 times 2 times 2 data. So they try to, there's no reduction operation, which means you just get the data. However, in reduction, you apply some operations. For example, as I said, accumulation. Is it clear now? Yeah. Okay, so for all gather, so basically it just composed of 2 phases. The first one is gather phase. So basically what you need to do is you apply this gather. Okay, so for example, each device, it has 2 times 2 matrices, and there are 4 ranks. And after this gather operation, for the root device, it collects the 2 times 2 matrices from each devices, and totally has 4 times 2 times 2 matrices. And this is the first stage. And the second stage, it broadcasts this 4 times 2 times 2 data chunk to each devices. So this is all gather, right? It's just simply a combination of gather and broadcast. The first basic communication collectives and the 4th basic communication collectives we mentioned here. And you can have more complicated communication collectives. And the first one is reduce scatter. So for reduce scatter, so it basically composes of 2 phases. The first one is reduce phase. So basically, let's say you have this each rank, you have 4 times 4. You have 2 times 2 matrix. 2 times 2 matrix. You first apply this reduction phase. So you basically do, for example, aggregation across different devices. And in the root device, you will get an accumulated 2 times 2 matrices. And you apply this scatter phase. So basically, you try to scatter this 2 times 2 accumulated matrix to each devices, such that each device only hold 1 element. Is that clear? Okay, so this is the reduced scatter. And you also have this all-to-all. So all-to-all basically means just data shuffling. So let's say for each GPU, it has different chunks of data. So basically, you just shuffle. For example, in here, taking an example of the first GPU, in here, you basically just receive the red part from different ranks of different GPUs and gather them together to have this big red data chunk. So this is all-to-all. So you can just understand this is more like an data shuffling. Let's say you want, so you have in your root device, you have different pieces of data, and what you want is you want to set some part of data to other devices, and you also want some data from other devices. So it's basically just a shuffling to do this. Yeah.
For the reduced scatter, would it actually be done in 2 phases, or would it just be like you send, like say the top row all goes to rank 0, then the middle row all goes to rank 1?
What's the question? Sorry.
Like, is it actually done in 2 phases, or is it done in one go?
It depends on the network topology, but basically the most common way is done in 2 phases. Yeah, it depends on the network topology. We will use an example in tutorial to explain this.
For the 2 phases, so one machine will do the reduction of all of them and then scatter it back.
Yeah. You will have a root machine, a root device to code these communication collectives.
What composition of base operations is used to achieve all-to-all?
It's basically just different. You can assume this different point-to-point communication composed together, right? So this all-to-all can you can also view this all-to-all as basic communication collectives, because most of these distributed library they have this all-to-all as a basic communication collectives, and they also have this all-reduce, which compose of 2 phases. Very simple. So you have reduction phase, which means you have these 4 different datas in each rank, and you do reduction. So basically, let's say you call this all reduce in the second GPU. So after this reduction phase, you don't have any data in the other 3 GPUs. You only have data in the second GPUs, and then you do broadcast to broadcast this reduced result to all other GPUs. So this is all reduced. So they are basically different communication collectives, and based on these different communication collectives, we will implement different power reason strategies to kind of divide our distributed workloads to different GPUs. Sorry. So based on these all communication collectives, so any more questions on this? Because it is very important to understand different power reason.
So the all reduce, just that first we choose one, we do the simple reduce, which is just here, and then we just copy it to the
broadcast to other devices.
So I understand like all the collectives have different pros and cons based on the topology.
Yeah, exactly. Yes. Different network topology, they prefer different communication collectives. So there's always a trade-off. So we will introduce later, because for different power reason, they require different communication collectives, and the complexity of different communication collectives also vary across different network topology. So you always need, for example, give you a distributed system, you always need to do some search to realize what is the best parallelism strategy. But at this point, we just need to understand what is the basic communication collectives because they are required when we perform different parallelism strategy. Okay, so the first parallelism is very simple. It's called data parallelism. So basically, you just need to split the data across the devices. So the assumption of this data parallelism is, let's assume one GPU can host one entire model. For example, in the early stage of convolutional neural network, one GPU can hold, for example, one ResNet. So let's assume you have, let's say, 4 GPU in your distributed system. So what you're doing is you just keep the entire model copy in each GPU, right? And let's assume you have n data points in your data set. You basically just divide this n by 4, and you have equally n over 4 numbers of data in each GPU. And you do training locally. This is easy to understand, right? So basically, what you need to do is first you distribute data to each local GPU, a single GPU, and then you in single GPU you perform local, for example, SGD, stochastic gradient descent. You get all these gradients and parameters updates, and in the end, you will need to apply this all reduce, which means, let's say, let's use an example of this all reduce. For example, for these 4 GPU, they all have different gradients to update. So what you need to do is you need to kind of reduce all these different, for example, you need to accumulate or take average of all different gradients calculate in each devices to calculate the final gradients you want to apply on your original model. So this is very simple data parallelism, right? So each device they compute the forward pass and backward pass of its own data. And this own data is a small portion of the large data sets. Any question on this data parallelism?
So is each device running its own set of data?
Yes.
The data is not like it's partitioned into 4. It's not like sample data or whatever.
What's the question? Sorry.
The data is partitioned into 4 like distinct.
Yes, exactly. And when you do this one round of local training, and the forward pass and backward pass, you kind of aggregate all these different gradients using this all reduce.
It's kind of like 4 parallel.
Yes, exactly. 4 parallel. Any questions? Okay, so the second parallelism is called model parallelism. However, in model parallelism, there are 2 types of parallelism. One is called interlayer parallelism. So the basic idea is, let's say you have a model, let's say 4 convolutional layers. This is your model, 4 convolutional layers. 1, 2, 3, 4. And what you're doing is you basically offload a small portion, for example, the first layer to this first GPU, and the second layer to the second GPU, so on and so forth. So basically, you distribute the one model to different GPUs. And the motivation of doing this is, let's assume you are going to train GPT-3 models, which has 175 billion parameters. This scale of parameter cannot be holding any single GPU, right? So basically, what you need to do is you need to split this model into multiple chunks, for example, layer by layer, and each single GPU runs small portion of this layer. For example, in here you have a data point, which is a data set. You have a bunch of data sets, and you fit into the first GPU, and you do your processing to process the first layer, and all the activation calculate after this first layer will send to the second GPU via a point-to-point communication, which we mentioned. This is one communication collectives, right? So on and so forth. So we have GPU1, GPU2, GPU3 to execute different layers. So let's assume we kind of equally partition one model into 4 parts. So each GPU will execute one part, and activation is flowing through this distributed system. So in contrast, this data point, there's no activation flowing through these 4 GPUs. They just need to aggregate all the gradients computed in the local GPU, right?
For inter-layer parallelism, does that mean that they can't compute at the exact same time? Because GPU 1 has to wait.
Very, very good point. So there will be some pipeline bubble, because when you calculate this GPU 1, it will need the result from the GPU 0, right? There's some cold start issue. So this is exactly what we'll introduce later. It's very interesting parallelism called pipeline parallelism introduced by Google. So as you can see here, instead of waiting for all the data ready and you pass to the next GPU, so you kind of introduce this micro batch idea. So you basically just, let's say, once you have some certain numbers of data ready, it doesn't need to calculate the whole data in your local GPU, just some portion of data. You can just immediately pass to the next one. So it can effectively reduce the pipeline bubble. This is the original one, and this is the later one. But this is the idea of pipeline. So this is a very good question. This is the problem of interlayer parallelism. So the next is intra-layer parallelism, or people also call it tensor parallelism. So why we need it? So this is because in modern large language model, even a single layer, it might contain a lot of parameters. And sometimes, when we're talking about very large layer, it cannot even fit in one single GPU. So look at this intra-layer parallelism. The assumption is one layer can be fit in one single GPU. And in this data parallelism, the assumption is one model can fit in one single GPU. And then we go to like more extreme case, even one layer cannot be fit in one GPU. So in this case, we need to partition this one layer across different GPUs. So this is why we have this model like inter-layer parallelism, or called tensor parallelism. Like an example is here. So let's say we have one layer. So basically contains, like say, when you concat them together, it's a complete tensor. But you can also split this complete tensor, one tensor, into 4 portions. And you kind of distribute each portion of this tensor to each GPU. And the idea is very similar to the, like in CUDA programming, we are talking about with tiling, right? So we try to split these big matrices into different small tiles. And the reason, the way we are doing is, for each tile, perhaps we assign it to different, for example, SM or different CUDA core. So this is the way we are doing tiling. However, in here, it's more like a more coarse granularity. So we kind of, now we are not manipulating on a single CUDA core or a single SM core. So we are trying to allocate this distribution in a granularity of single GPU level. So this is the idea of tensor parallelism, and I use an example to explain this. So this is the matrix multiplication example we visited before, right? So this is A times B, and you got C. So the tensor parallelism means, for example, in this A, you partition this A into 2 parts, and the same for B. And you kind of distribute different parts to different GPU to do this tensor parallelism for this performance. And for this tensor parallelism, you need to be careful because you need to do reduction operation. For example, in here, you got different, like let's say you do this this separation of two different to separate one single matrix into two portions. And when you do this like orange part, let's say this orange part, you calculate in one GPU, and the green part you calculate in another GPU. And these two, the result of these two parts, they need to accumulate together to get the final output. This is the problem we mentioned before, right? So that's the reason why in tensor parallelism you need an all-reduced communication collectives to collect all different intermediate results from different devices to get the final outputs. So this is the tensor parallelism, and this is the figure of how when you apply this tensor parallelism, how this computational graph or this network structure looks like. So one thing I want to mention is, for example, if you don't look at this green part, F, this is just a normal self-attention module, right? You have a layer normalization followed by self-attention, linear layer, and dot product. And if you apply this tensor parallelism, when you do the forward pass and backward pass, you need to insert these different communication collective operators. And in this case, as I mentioned, for tensor parallelism, you need to do reduction operation. So you basically, for F, when we look at this forward pass, F means no operation in forward pass. So you don't need to do anything. However, in here, after you do this tensor parallelism, you need to do all reduce to do a reduction, right? And this is the operation in forward pass. And in backward pass, it's kind of a conjugate operation. So basically, you don't need to do anything in this block, but after this gradient update, you need an all reduce operation in the backward pass. So that means if, let's say, you construct a neural network graph like this, and when you want to perform this tensor parallelism, you basically need to insert some communication collectives before and after the layer you want to apply this tensor parallelism. And this communication collectives, for example, F, these two F, they are conjugate operation in backward pass and forward pass. And the basic idea why they are conjugate is because it's very easy to understand, right? In forward pass, so you kind of split these different tensors to each devices, and in backward pass, when you get gradient, you also need to collect them together. So it's more like a conjugate operator.
Is there no function that you put to say that you're splitting the data in the first place?
Yeah. Yes.
So where would this be on?
Yes, it will be like included in this app. Yeah. So this is tensor parallelism. If you don't understand this figure, that's fine. But just ensure you understand for this tensor parallelism, what you basically need is even a single layer cannot be fit in a single GPU. So you need to further separate this layer into multiple different GPUs.
Is this just weights being divided? It's not activation?
Yeah, it depends. All depends. You can also divide the activations. Okay, so one of the issue of tensor parallelism is the data dependency. So recall what we have introduced in the first lecture. We have a softmax, so it kind of have a row by row dependency. So we're not able to do this kind of partition, right? If it has row by row dependency, we need to have some extra statistic to track this normalization statistic. So this is the problem of when people are applying this tensor parallelism on modern large language model, they realize this like some operators very restrict their their partition dimension. Like you are not able to separate this matrix along the column dimension. So people also propose this sequence parallelism. So the key idea is very simple actually. So let's say you have different tokens. In your token means input in large language model. Maybe you can just imagine this is one word generated by large language model. So these different tokens are distributed to different GPUs for processing. So this is another dimension of partition or parallelism, which means when your model has some restriction, for example, a data dependency, which kind of might stop you to do tensor parallelism. Another alternative is sequence parallelism. You basically just distribute the whole computation associated with one token to different devices. And in this scenario, you might need to have different copies of weights across different GPUs, right? So this is sequence parallelism. And when we combine this sequence parallelism with this tensor parallelism, so in this sequence parallelism, the required communication collective is scatter and gather. And when you combine this tensor parallelism with sequence parallelism, you will get this G in your paragraph. And this G means the all gather operation in forward pass and reduce gather in the backward pass. So I will list as the homework for you to think about why this G is the all gather and reduce scatter. So think in this way. So at this point, what communication collective required after the sequence parallelism, and what communication collectives required before parallelism. And you basically just combine them together. For example, again in here, what communication collectives required after this tensor parallelism, and what communication collectives required before sequence parallelism, it will lead you to the answer. And in modern large language model, there are different types of parallelism called expert parallelism. So this is more advanced knowledge. So it basically, so the MOE architecture is basically like this. So you might have different feed-forward networks. And during the runtime, you kind of have a controller to control which path, which feed-forward path you will choose, which linear layer you will choose. So this is kind of runtime decision. So the expert parallelism means, for example, at this point, you know, for example, in this point, you know, for example, the first token and the third token, they will execute the first expert. So you basically just kind of collect all the tokens, will choose the first expert to ascend GPU. And let's say in this case, there's other tokens, they choose the second expert. So you basically just offload different computation to different GPU, and each GPU holds the parameters for different experts. So this is called expert parallelism. It's more common in like very large language model, because if you check the leaderboard of large language model, so for a very big model, let's say over than 100 billions, they usually have this MOE module. So to execute and optimize this MOE module, you usually need this expert parallelism, which means at runtime, for different, in your data batch, different tokens, they choose different expert. So you kind of dedicate a different GPU for different expert, and you just kind of send different tokens to different GPU, which holds different expert.
Does that make this more challenging than the other forms then? Because like with tensor parallelism, for example, you kind of know the whole communication topology up front.
Yeah.
Whereas here you only...
Yes, there will be there are a lot of workload imbalance problem in this situation, and there's some active research direction exploring this. If you look at all this latest research published in the top machine learning system manual, you can see a lot of papers exploring how to mitigate this workload imbalance in expert parallelism.
Training time with the mixture of experts, does the model kind of figure out which expert's which, or do you feed different data to kind of?
So the data, so they have a module which will take the input and decide which expert. So it's kind of basically depends on the input and depends on your weight. So it's make it very unpredictable, right? You don't know what the data is. You don't know which experts you are going to activate. So this is the reason why this will kind of cause a lot of unbalanced execution, because if let's say if this is your first GPU and this is your second GPU, so they kind of, if let's say in here you need to execute 10 tokens, and here you just one token. So which means this GPU will kind of keep waiting for the first GPU to finish. So this is kind of another pipeline bubbles introduced in this mixture of expert. And one extra information we got, so we actually have a PhD working on this topic, and we also found different models, they actually have different expert activation distribution, which means for some models, they are very evenly activate expert. But for some other models, they will have a lot of skew. For example, they tend to often choose the first two actions. So this kind of effect of this expert parallelism depends on your models.
So is it therefore not that common, if you've got this variation, to regularize the training of the router to kind of penalize always favoring one expert?
But you need to change your algorithm, right? You need to change your model. Is that what you're asking?
Well, so if, like, my assumption about the way that you'd make it kind of decrease the imbalance is at the point that you're training the router, you have some regularization term that
that is one way to
but not everyone does that.
That might affect the algorithm because it requires you to train this router, retrain this router. But this is one way to do algorithm hardware co-design. If that's you apply this regularization to make these more balanced, you might hurt some algorithm. You might need to retraining. So this is a very good example. So so next one is pipeline parallelism we introduced before, right? So in the interlayer parallelism, so for example, when you distribute different layers across different GPU, and each GPU, for example, needs to process 10 data. So the naive interlayer parallelism is you need to flow this activation across different GPU. So you you first need to wait all these 10 data in the first GPU to process the first layer, and you pass all the activations to the next GPU for the next processing. It will kind of have a lot of pipeline bubbles, which means a lot of resources are wasted or are kept idle. So Google actually introduced an optimization called gpipe. So the key idea behind here is, so instead of waiting all 10, for example, 10 data points to be finished in the first GPU, why not just send the data, the activation right after the first data point finished? And you do this in a pipeline manner. Let's say you finish the computation of the first layer of the first data point, you send it to the second GPU. And in parallel, the first GPU will keep processing other data. And because you have this the data from the first GPU ready in the second GPU can do the same pipeline. So this kind of significantly reduce the pipeline bubble. So this is called parallelism pipeline. And as you can see in this slide, different parallelism, they are requiring different communication collectives. So for example, so for data parallelism, so it requires all reduce. And for tensor parallelism plus the sequence parallelism, it requires all together. So coming back to the question we asked before, so what decides which parallelism we should use and which communication collective we should use? So the logic is like this. So the parallelism strategy plus the network topology decide your communication collectives. So this is the key design parameters you need to consider when you design this distributed machine learning system for training. You need to decide what is the parameter you will need. So there's some active research along this direction. And the key metric to measure the effectiveness of this distributed machine learning system is, for example, the memory consumption. And the second, the communication overhead. Because these communication collectives also incur different overheads in different network topology. Because your network topology can be all-to-all, which means different rank is directly connected to different to all other ranks. And there's another network topology which we call ring topology, which means like they are connecting one by one. So like one device, they all connect to two adjacent devices. And in that case, different communication collectives will also incur different communication overhead. And we will use an example in our tutorial question to explain why different communication collectives will incur different communication overhead. Okay, so this is more complicated scenario. So this is from the Megatron. So this is very latest large language model paper. They try to combine different parallelism strategy together. So the key, I will not introduce this paper here because it might need another 10 minutes to introduce. But I still want to put the slide here so you can click this paper link if you are interested to look at. And the key point I want to mention here is basically after we know all this basic parallelism strategy, the best distributed parallelism strategy is always the combination of different. So it's basically a design space you will need to explore. So this is also some research published by Microsoft. So what they are doing is, given the large parallelism strategy, let's say the design space is very large, they try to search this parallelism during the runtime to determine which parallelism combination is the best. Okay, so until now we cover the distributed machine learning training in terms of different parallelism strategy and like what is the main concern? Like when we decide this different parallelism strategy, we need to consider memory footprint, communication overhead. And next, we'll introduce some other concerns. Let's say in here, this is your distributed learning system. There are many different aspects. So first one, you need to consider the performance. So you try to search what is the best parallelism strategy given your distributed system. And there's another aspect you need to consider, for example, the data privacy and the scalability. So the next we'll introduce a technical federated learning. So the idea of federated learning is basically decentralized training. So in all the example we introduced before, we will have a central server which collects gradients from different distributed GPU nodes. So there's a kind of centralized training. So in federated learning, the key idea is here. So in centralized training, it basically contains two steps. The first step is the clients send the data to the central server. So basically, for example, in here, you are a client, so you send the data to central server. You have different, assuming you are different clients, you have different types of data you send to the central server. And this central server performs this training. And one issue of this centralized training is data privacy. Because in this process, you upload your data to a company server. So one example is, for example, when you use ChatGPT, you have the option to click whether to share your data to improve the model capability. So this is kind of the concern of data privacy because you upload your personal data to the company to do this training. And the idea of federated learning is to consider the data privacy in this centralized training pipeline. So the key idea is instead of sending the data here to the central server. So we kind of just set the gradient to the central server. So this is the key idea of federated learning. So you still keep your data in local device, and you just set the gradient back to the central server. So it basically contains still, I summarize here, 4 stages. The first stage is the central server send the model to client. So each client will have a full copy of your central model. And the model try to train this is on train on the local device using its own data, right? So different clients, they have the model copy, and they just train on their client side. And then after get the gradients, each client send the gradient back to the central server. And central server only is in charge of the gradient application. So this is federated learning. So the reason why this can protect privacy is because no data is transferred to the central server. And this is the very basic implementation or the initial version of federated learning. So it's called Fed average. So I was planning to use this Fed average as one of our paper reading material. So the idea of Fed average is very simple. So it's basically following the process we described before. So each client send a gradient. And in Fed average, they just average all these different gradients received from different clients and apply this, for example, aggregation and update the central server and do this another round of model updates. And as you can see here, the key idea is in each client, we apply the local SGD. And on the client side, we do this weighted averaging. So this is and this weight contribution is proportional to the local data size. So for example, if one client's they kind of use this gradient, they kind of use 10 data points to calculate this gradient. So during the aggregations stage in the central server, we will count more of this gradient compared with other gradients, for example, calculate in other clients just using one data point. So this is kind of weighted averaging, and the weight is decided by how much data you used to perform your local SGD. Any questions on this? Yeah, so basically in federated learning, we don't need to know too much, just the whole idea. We kind of transfer the gradients. And the key problem of the federated learning is how to do this aggregation and how to do this local training. And there's one thing I also want to mention is more like terminology. So perhaps if you are looking for some job related to federated learning or some interview questions, so there are 2 types of federated learning. One is called cross-silo, and the other one is called cross-device. And the difference between these 2 federated learning paradigm is the cross-silo is mainly like across different institutions. For example, different hospitals, they have like very large amount of data, and they have the fewer, like very large of local data in each hospital, but they have fewer participants because perhaps you only have 3 or 5 hospitals to join this federated learning process, and the system reliability is very high. However, in cross-device federated learning, so this is more like individual clients. So all different clients, they have their personal data can upload. So basically, for each client, it has the fewer data size, right? And for you might have a large pool of clients to do this federated learning. And for the system reliability, because we're talking about the institution versus the individual client, so the system reliability of the institution is better than the clients because maybe some clients, they may run out of battery sometimes, or the network is not so stable. However, in institution, it's more stable. So I try to compare this cross-silo and cross-device into these different dimensions, so you can easily compare what is the key difference of these two approaches. But to very concise describe their description is cross-silo is more like cross-institute federated learning, and the cross-device FL is more like cross-client federated learning. So whereas a cross-client, it's more like individual client, and you have a large amount of clients joining this federated learning process. And another extreme case of federated learning is called model merging. So in this federated learning, we also need to have this frequent synchronization between clients, between central server and local clients, right? We need to aggregate the gradient from different clients, and after this aggregation, we need to send the updated gradients to each client. So this is kind of iterative process. However, in model merging, it's kind of an extreme case of federated learning. So which means there's no communication round. So each client only train the model on its home data, and we just do one aggregation towards the end. So this is an emerging technique called model merging. So yeah, let's take 5 minutes break, and we will come back. Yeah, it's a very good question. So in the literature of model merging, there are two categories of one is called information-based, and the other one is called information-free. For information-based model merging, you need some statistics from your pre-trained stage to know guide you how to do it. And usually, like they do, if they propose one model merging approach, they will do these two types of benchmark. But usually, if you have some information, you expect to get higher performance. Yeah.
Trusted.
You want to go?
Every single client has to have hardware that is capable of doing the entire.
Yeah, exactly. Yes, that is the assumption. Yes, but I think so my supervisor when I need to. At the university, so they try to also apply different how is the structure is better. Yes. But it's very challenging because you Yes, exactly. But I think they want to approach 7 billion more. I think they released some more of them. So I just checked flow labs.
I mean, we'll keep
So if you hit N,
Yeah, I have done this.
But then
You take quantum already?
good luck.
Thanks.
Have you been sitting there this whole time?
Yeah, I came in like 3 minutes late, and then this girl was there, so I couldn't squeeze in.
Lunch today, or are you gonna go to study? Okay.
Lunch. Like avoiding studying so that my brain power doesn't get used up.
I don't know. Dinner. Tomorrow. Oh, we're gonna meet up. Maybe. Yeah. I'll be there.
Like 8-7, is it? PM tomorrow? Second course. Or it's only one course? Okay.
Yeah. And I feel like the pacing of like this term for me, like everything is just like, and I don't know.
Right now I'm like behind on scheduling, 3 scheduling tutorials. I haven't done the RL tutorial.
Oh yeah, I haven't finished the one. I like was there for the first 2 hours.
Yes.
I started the coursework. I was like going really slow because I was trying to review some random. I did review 30. I did like just like the first lecture part of the coursework. I don't know how big the market. I'm last because like I haven't there's just I still have coming but then after I submit tonight all day Wednesday I'm just gonna try like this past weekend I was like catch up on there's like one for every single lecture so I like felt pretty I released 3 of them just like you like just forgot to release some then you release all of them. I've like looked at all of them. Pretty much. So I'll have like I kind of want to go to conference tomorrow, but I feel like it's gonna be bad because like everything. I have like a lot of questions. It's
gonna be like. That's my brother.
He's too smart. He doesn't do the problem sets.
Finish it.
But I mean, it is true though. Like, they're probably like
not all the short time that I'm going it's a bit stressful. Like,
I like
what I've heard, and then mine's like.
I feel like some of the problems are like I don't actually understand. I just like monkey around. I'm like, oh, like these are the steps we learned in lecture. I'm just gonna like execute the steps, but I don't know. Like I do. Like not to the intuition.
This is not complex. I literally just use the technique.
All the problems kind of like follow like a similar.
Didn't make any sense. No.
Just like I feel like I mean good for like getting smart.
It might be
this.
He obviously understands. He's not telling you, but he's Spanish. He's telling me Spanish. It's very clear, like when you send me like. Write the question. So like because I've had 2 tests already, so like it's accent. So it should be like an English and the grade, which is if you write out the thing, you should be able to solve it. That makes so much more sense. So like why darn hard, and that's like very. Sometimes like HA is just shouting, and then they're just no. Looking at it like convention, so like I would have done it like on my own, that kind of thing. Like, and even sometimes like I would know what's tests, like I have no idea. So those are like. That's ha English we use. But the quantum is very clear, like which are the reserved for the A students and the 20% which is reserved. I don't know if the math for ML feels similar to like there's some questions that are clearly not meant easy, some that are supposed to be doable, that kind of thing.
It is nice. You started labeling all the problems on the project based off of difficulty. Adds notes where he's like, This is good to like understand. But like,
I would squeeze that. A public figure. See you later.
Yeah.
That's like the shortest.
Hi, welcome back, everyone. Can you hear me?
I guess like if you're randomizing.
I see that the way that.
Yes, I want to finish as early as possible to let you to have lunch. So let's start earlier. So this is we introduce different distributed training. So I introduced different communication collectives. I introduced different terrorism strategy, and I introduce apart from this performance concern, we also have data privacy concerns. So we have federated learning and model merging. And the other topic we will cover today is distributed inference. So the reason why we need distributed inference is because the emergence of large language model. So previously, when let's say in the time of ResNet, people are not talking about distributed inference because, as I said, one single GPU is always enough for a full model. You don't need to do this distributed training. However, when we are saying your model, one model contains up to trillions parameters, even in the inference stage, you also need to distribute different computation to each GPU. And recall, there are several tutorial questions in our past tutorial session. So we calculate the amount of parameters required or memory footprint required for inference and training. They are different, right? And for the training, it's more memory intensive. And for this inference, even this is less intensive. When we are talking about very large models, we still need to distribute the computation to each GPU. So to introduce this idea, let me just briefly introduce what is the inference pipeline of large language model. So the inference pipeline of large language model is usually composed of two stages or two phases. The first one is called pre-fill phase. So for example, you have a large language model, you ask this large language model question. So all your questions can be in parallel feed into your large language model for parallel execution, right? So this is called pre-fill stage. We also interpret this as they try to encode the input prompts, and this input prompts contains a sequence of tokens. So it allows parallel processing. For example, this is your prompt, the quick prompt box. So because all these tokens are given by user, right? This is the question you give to your ChatGPT. So they do this in parallel processing, and they do this pre-fill stage. And then they do this decode one by one. So in this stage, there's one thing I want to mention is called KV cache. So in here, in the pre-fill stage, you generate different KV vectors. And you don't want to recompute all these KV vectors. So you want to cache these KV vectors. So you just, every time you do this pre-filling, you will generate a bunch of KV cache. You don't want to recompute. And as the decoding goes, so you have more tokens are computed, and for each token, you will add one entry to this KV cache to cache them, which means you don't need to recompute all the KV entries for all previous tokens you processed. As I said, pre-fill phase is the first phase. You kind of parallelly process all the token, which is also the question you get in your ChatGPT. And the second stage is called decoding stage, which we called autoregressive generation. And recall the first slide, what we call is, so this existing large language model is basically encoded on the architecture, but they try to enforce the causal mask for this processing. So in decoding phase, it kind of generates token one by one. So it's kind of the autoregressive generation manner will cause a lot of memory issue. So this is a roof-line model. So we introduced in the first slide. If we try to understand the characteristic of pre-fueling stage and decoding stage of our large language model, you realize they have totally different roof-line models. So basically, let's say, assume we have a GPU with this turning point and the peak performance and the memory bandwidth. So this is our model. So for decoding, in the decoding phase, as I mentioned before, so it generates token one by one, which means it loads all the weights, for example, from off-chip memory. It only generates one token. So it has very low data reuse or weight reuse rate. So you you load, let's say, billions of weights to just generate one token. So it has very low data locality, so which means it has low operational intensity. Remember the definition of operational intensity? So the characteristic of pre-fueling decides is sometimes always kind of sitting in this area of this roof-line model. So it's heavily memory-bound workloads. And in contrast, for pre-fueling, so you actually can process multiple tokens together. For example, your question contains, for example, 1,000 or 100 tokens. So you can process them together. So you can understand this as you load, let's say, billions of parameters to process thousands of tokens in parallel. So it basically has the higher operational intensity, right? This is easy to understand. So they kind of have different computational, or in this roof-line model has the different computational characteristics. So for memory requirements, decoding usually is more memory intensive, and for preview stage, so a preview is usually like more. I would like to say it's less memory intensive, and if let's say you have a very large batch, very high data parallelism, so you basically is kind of compute intensive. So this is two phase of our large language model generation process. It has two phases, and one is called prefueling. It's basically, and most of the time, compute bound, and decoding, and most of the time, is memory bound. This is knowledge you need to remember. And this idea of the idea I want to introduce is called it's first proposed by Microsoft. So it's called splitwise. So the key idea is we realize in this large language model processing, it contains two phases, and this two phase has totally different characteristics. One is memory bound, one is compute bound. So in this case, as we know, so to achieve better performance, memory bound prefer some GPU devices with higher memory bandwidth and capacity. And for compute bounds, it prefers some GPU with low memory bandwidth, but with high computational intensity, with more computational resources. So the idea of splitwise is, let's say we have a distributed system, which is shown in here. Like we have, let's say, 100 distributed GPUs, and this kind of GPU pool has different types of GPU. For example, you have H100, you have A100. And for example, when we're comparing H100, this is more, it offers higher memory capacity. And for A100, for example, it offers less memory bandwidth. So in this pool, we try to separate this distributed GPU into two different types of machines. The first one is called prompt pool, and the second one is called token pool. So the prompt pool is used to process this pre-fueling stage, because the machine in this prompt pool, they kind of have the good, compared with the token tool, they kind of has the less memory bandwidth, lower memory bandwidth. And for this token pool, for example, you are using, let's say, H100, H200, they have the higher memory bandwidth, and you use all these machines for decoding phase. So basically, you try to the key idea behind it is disaggregated acceleration, which means you separate your workloads into different stages, and different stage will be offload the different types of machines for disaggregated acceleration. So this is the key idea of splitwise. So as you can see here, apart from token pool and the prompt pool, they also introduce a mixed pool, which is used kind of as a buffer pool. Let's say if for some emerging incoming workloads, it has more requests of pre-filling stage, so we'll kind of assign some machines from this mixed pool to reassign some machine from this mixed pool to this prompt tool. So it's more like make this scheduling and clustering more flexible. So this is the key idea of splitwise. Based on the workload's characteristic of your large language model computation, you assign different phase to different machine. And in this work, it's basically, you can see one of the key bottleneck of this work is KV cache transfer. As I mentioned before, in this prefill, after this prefilling, you generate a lot of KV caches. If it's in the same GPU machine, that is fine, right? You don't need KV cache transfer. You perform prefill and you perform decoding on the same GPU. However, if you like perform this disaggregated acceleration, you perform prefill in one machine, and you need to transfer your KV cache to other machine. It actually introduces some overhead, right? So this is one problem introduced, mentioned by this paper, splitwise. And the approach that addressing this is, we already visited multiple times. It's called pipelining. So the key idea is, in here, instead of waiting all the KV cache generated ready towards the last layer, why not just transfer? Once you have the KV cache of one layer ready, you just transfer to the other devices. So this is the key idea. So they use this idea, like pipelined KV cache or more fine-grained KV cache transfer to reduce this pipeline bubble. And the idea is very similar to this pipeline parallelism, right? So you don't need to wait the KV cache generates all the KV cache generated. You can just transfer any KV cache generated by any layer. And once this layer is finished, you just transfer to other devices. And there are multiple different metrics to evaluate the performance introduced by this technique. For example, here I list two most representative metrics to evaluate the performance of large language model inference. The first one is called time to first token. So the reason why we need this metric is because it's usually measure how fast your pre-filling stage is, right? So because at the beginning we fit all our prompts into this large language model, and we do this pre-filling stage, and we generate the first token. So this time to first token is representing the speed of your pre-filling. And we also have end-to-end for end-to-end latency. So this end-to-end latency, when you divide by the different, when you divide this end-to-end latency by the total number of generated tokens, you can get the average latency of each token. So in splitwise, they try to use different clustering strategy to compare the difference. So in here, for example, 55P, which means 55 prompt machines, and 15T means 15 token machines. And you try the different combination of this prompt machine and token machine, and like they try to evaluate the scheduling approach they apply in this paper, and they can see the significant improvement in this overall performance in both TTFT and end-to-end latency. And one key problem of this paper is it's all based on simulation. So there's no actual system. So it's more like simulation-based research to demonstrate, okay, this idea actually makes sense, and we should go forward in that direction. And after this work, several months after this splitwise, which is based on simulation level evaluation. There's another work called DistServe. So it actually implements this idea on multi-GPU pools, multiple GPU pools. So they can actually see the real benefits. And I think in last week, the group of this server, they tried to review some statistics showing in real industry setting, it actually bring a lot of performance benefits, including the energy saving, and for example, this slow the service level objective, which reflecting the user experience. So they try to release some statistics to demonstrate, okay, this technique, when applied in real GPU system, they can improve the user experience and reduce power consumption. So this is the disregarded, I will not go into too much detail of this, but the key problem of this, when they try to deploy on the real GPU, is you can always formulate this as a placement problem. And this placement problem is actually deciding how should I assign one particular prefilling workloads or decoding workloads to which GPU machine in your pool. So they formulate this problem as a placement problem, and they try to resolve this problem. And as you can see here, they can achieve better performance. So I won't go into too much detail here because this is not part of the exam. And so the last part is the performance scaling of large language model. So I believe many people heard about the scaling law of large language model. So this paper is released by OpenAI back to 2020. And at that time, people were still actively exploring techniques such as neural architecture search. Let's say, given a certain amount of parameters, how should I design a better architecture? However, this paper, the key message they want to convey is the key factors to affecting your neural network performance are, first, the amount of compute you used, which is related to your training time. The second, the size of data, how many data you have. And the third, the model parameters. So one of the key message they convey in the paper is the performance depends very weakly on all these architecture parameters. For example, the depth, how depth the architecture is, what is the kernel size. So these always have parameters. They can introduce minor performance if you are talking about at a certain compute budget. However, if you really want to scale in the performance of your neural network, what you need to do is first increase the training time or compute time used for training. Second, make your model larger. And the third, scale your data set.
Wouldn't the other compute hyperparameters be kind of proportional to the amount of compute?
Sorry, say that again.
Won't the compute hyperparameters that they say it depends weekly on, aren't they proportional to the amount of compute?
Yeah, so I think the key message here is under the certain compute budget, different hyperparameters might only introduce very minor improvements. This is the key message. And they try to, this is very, this paper, they provide a lot of empirical experiments. And this is the conclusion they got. So later on, people referring this as the scaling law of large language model, which means to get the very good performance of large language neural networks, basically scale your model size. So you can see now we have this trillion parameters models. And the second, get more data. And the third, training longer. So this is back to 2020. After that, there's another 2 years later. There's another paper introduced by DeepMind. So it's basically still agree with this opinion. If you want to improve your model performance, you still need to scale your model size, still need to scale your compute, still need to scale your data. These three are still the key factors. However, what they want to, the key message in this DeepMind paper they want to convey is, when you have a certain budget of computation, so how to allocate these three factors. For example, if you have a certain compute budget, one way you can do is you design a very large model and you train in less or fewer epochs or training times, right? So for example, you have 70 billion parameters, but you can only train one day, given a certain compute budget. And the other way around is, you kind of have this smaller model, let's say 7 billion, but you can train this longer because, as I said, the compute budget is the same. If you get the smaller models, you actually have more time to train this under the same compute budget. So they try to enhance this scaling law from another perspective is, if you have a certain budget, what is the best strategy to allocate or balance the model size and the training time? Here, they're referring to the number of training tokens. You can basically just understand this is the compute budget, the training time, the training hours you can get. So the conclusion they got is, for every doubling model size, you need to, the training tokens should be also doubled. So this gives us some guidance on, let's say, when we have a certain GPU hours, let's say we only have 100 GPU hours. If we want to get a very good performance large language model, how to allocate this model size and how to allocate this training time. So it's like you need to decide, they're balanced. You need to design this trade-off, right? So this is people are also call this as the chinchilla scaling. So they are all referring to the scaling law of large language model. And this is the Xinurval's keynote last year. Ilya, so he's the co-founder of OpenAI. So they put this slide in his keynote. So the pre-train, as we know, it will end. So basically the key point he wants to mention is we are not able to get more data to keep this, remembering the scaling law introduced in 2020 by OpenAI. So they mentioned there are three key factors, right? Model size, training time, and data. However, if you don't have enough data, which means you cannot keep this scaling law improving. So what comes next? So there are several possibilities. The first one is synthetic data. So can we generate the synthetic data to kind of keep generating more data for keep this scaling law of large language model? And the second, people are talking a lot about embodied AI, which means, for example, you use your robotics to interact with the real world. So it's another way to kind of generate more data, right? So you kind of use, for example, robotics to because, for example, you have a camera, so you kind of keep collecting data. So this is another way to kind of collecting more data to keep your scaling law remaining. And the last one is inference time computation. And this is also the next one we want to discuss. So now we can see the diminishing return of or end of the scaling law. Like we allocate a lot of compute resources on model training. However, if we have a certain budget, is this like, should we allocate all this compute budget only for training? The answer is not so sure, because as we can see, so we can see the end of scaling law of large language model training. So there's another direction of research. It's called test time scaling. So this is very famous. So this DeepSeek-R1 early this year. So they use the reinforcement learning to enable this test time thinking. So this technique is already introduced by OpenAI, but the DeepSeek team, they are able to reproduce this and open source this, which is kind of groundbreaking techniques, open source techniques. So the key idea is, instead of allocating my compute budget during the training, can we just allocate some of the computation during inference? For example, if we are talking about test time reasoning, so we have a long reasoning trace. and the large language model is able to think longer to make the decision before they make the final decision. So this is the key idea of test time scaling. You try to allocate more compute budget during inference time instead of just the training time. Is that clear? Yeah, so it basically just teach the language model to think more, to use more tokens during the runtime, during the inference time, to make the better decision. So this is the test time scaling. And there are two approaches. The first one is called internal scaling. So internal scaling means all the approaches similar to like this DeepSeek style reinforcement learning approach. They use a reinforcement learning to enforce your model to think longer during your training, during your inference. And the other way is called sample-based training. So it's kind of orthogonal to this internal scaling. It's more like during your training, instead of just generating one inference trace or one set of outputs, you can generate multiple outputs in parallel, and you can use some post-processing to select the best solution. And one example here is called best-of-n sampling. So this is the first and very naive sampling-based test time scaling. So basically, given the large language model, you ask this large language model a question. During this generation phase, it will generate multiple outputs. Let's say you ask what is contained in this image. It might generate, for example, 10 answers. And all of these answers referring to, for example, a cat. And after a majority voting, it will choose to predict the cat on this image. So this is the best of n sampling. And the other approach is called Monte Carlo tree search. So they basically formulate this problem as a tree search problem. So at each step, it will decide whether to kind of generate more token to do some branch out and to do some parallel thinking. So at some point, it will also do some rollout and help this MCTS to make a decision which path I should go. So another emerging techniques in this test time scaling is called reward-guided test time scaling. So basically, you kind of use a reward model to evaluate which generation is better. So remember, in best of n, we just use a majority voting right. However, this is not so good because you just use the answer with the appear the most. However, a better way is you deploy another model, and this model will kind of evaluate all the generation candidates you generate, and you use this large language model to decide which candidate you should choose. So it's more like the test time scaling is getting more complicated. At the beginning, we want to sample more, and now it's getting more complicated because we are generating different trees, and we kind of apply different tree algorithm on this problem. And later on, we also introduce another reward model. And we use this reward model to evaluate different samples generated by this large language model. It's getting more complicated. And this is all I want to, all this already covered the three parts I want to introduce. And there's some few slides, which I will need to open another PowerPoint. Give me a few seconds. Yes, so so this is the last lecture. So here in the last lecture, the last part I want to mention is in this lecture, I hope all the knowledge taught in this lecture is not just specific to this machine learning system and hardware. It's actually most of the idea behind these all techniques is also general enough to different problem you will meet in your future, for example, research or your job in industry. For example, the first one is with the end of Moore's law, we need more and more domain-specific optimization. And in this module, we use the example of TPU. we're showing, okay, so we are not able to rely on this technology, like the node technology iteration to keep the performance improving. So we need to have some domain-specific hardware. So this is not just applicable on machine learning. For example, in the future, you want to apply on other like bioengineering applications. This is the same. The key idea is just to design domain-specific architecture for the application, for the target application you are talking on. And the second is use the abstraction to simplify the design and program. So this can see in our MLIR example we introduced in our module. So basically, if you want to have some very focused optimization at some level, so basically the one way you can do is at each level you introduce one abstraction and you just manipulate this optimization on this level of abstraction to do, and you can have this gradually lowering philosophy in your framework to iteratively, gradually optimize in different abstraction level. And third one is make a common case fast. So this is another point I really want to share. So this is the reason why I want to introduce this NCU profiling in our coursework. So basically, if you have a target workloads and platform, if you want to improve the performance, the first thing you always do is do some profiling to identify which component is the bottleneck, and you should aim for optimize this bottleneck part. Because, for example, you have a workloads and you realize one component or one computation takes 90% of time. So you should focus more on that 90% of time of the computation instead of just wasting time on the rest of 10%. So this is the thing I want to mention. Make a common case fast. It's not just applicable on this machine learning system optimization. It's any system you want to optimize in the future. And there's some other philosophy you also need to learn, like performance improvement via different parallelism, pipeline, and prediction. So I think the parallelism pipeline are very straightforward to understand. For example, in this module, we mentioned different parallelism strategy. And let's say we're talking about a distributed large language model training or inference. We combine different parallelism strategy to achieve or improve the performance. And pipeline, which we have at least in today's lecture, we introduce how to use pipeline to reduce the pipeline bubble rate. So it's more like how to apply this pipeline in a fine-grained manner to reduce the hardware inefficiency. And also the prediction, like in traditional computer architecture, you have the branch prediction, right? So this is somehow all these techniques I want you to, after this module, I want you to then not just limited in this machine learning system. It's more general design principles. And I hope let's say in the future, you have some other workloads want to optimize. You can come back to this module to see, okay, whether one of these principles is also applicable in the future problem I have. And you will realize when you read, let's say, up to 10 to 100 papers, you will realize all these different latest research papers, they are just a combination of different philosophies. And you can also see this hierarchical design, how to make our memory system more hierarchical, and how to have this dynamic static approach. So all this philosophy, all these research ideas, and the latest research trend is also a combination of different design philosophy. And I really want this module is not just exam mark in your final record. It will be just help you to solve the problem in your future research and jobs. And the thing I want to mention is the mock exam will be released next week. I'm sorry for the delay because this is the first year we have this module, and I need approve from the department to approve the real exam paper, such that after they approve that, I can proceed to prepare the mock exam. Otherwise, I'm not sure whether the mock exam will kind of very related to the real exam if they ask me to change the real exam. So the mock exam will be released next week, and I will not make this very difficult. Ensure you understand all the tutorial questions. I'm sure you will be fine. Of course, I will still introduce, for example, 10% of question, which is very challenging, and to reward some student who really spent a lot of time in this module. But I believe for most of you, if you understand all the tutorial questions, you will be fine. And in the last, I want to thank you everyone, including the GTAs. They helped to build the evaluation platforms and help to set up this coursework. And also everyone in this room and maybe online or who didn't come, because in this year, this is the first time we run this module, and we have 157 subscriptions in this module. It's a large volume. I believe most of them didn't come today, but I think it's still really appreciate for your engagement and participant. I actually read every either email or your comments in the Ascend system. I really want to improve this coursework, and I really receive a very valuable comments in my module. So yeah, again, thanks for everyone's participation and engagement. I really appreciate it. And this is my first module. I hope next year we will make it more exciting. So thanks everyone. Thanks. Yeah, so I guess this is the end of today's lecture. So on Tuesday we will have a tutorial. And yeah, I will post the voting in the website to decide which one we should choose. Thanks.
Good, no?
Recently started. 3 weeks will take more than
Yeah.
Zahmet var. Neyse.
I'm an expert at
Emraz, actually. So this is actually audit. Like a diffusion language model for my Emraz. Okay, very nice. So it's mostly, it's not computer science. He's actually earth sciences, physics. For symbolic regression. So symbolic regression, genetic algorithms is the mainstay, or used to be. Neural network, autoregressive, and diffusion might be the thing.
I want to find. You said the new one at Sumada is multimodal understanding.
But that's true. It usually that does both. Because
it's good to
choosing
so much work. So much work. I'm doing discrete as well. Discrete for text. Yeah, exactly. I guess it has to do discrete for image because it's doing discrete for text. Okay.
Yeah. There was another paper. I know. I still don't understand how you do modal generation.
Something was happening.
Okay.
I know it's very big.
By the way, like continuous text isn't an impossibility. Like you can actually, like latent, outside like latent reasoning and all that. So there is a thing where you can actually have continuous probabilistic text. It's you have to snap it to a token in the vocabulary afterwards, and that's where a lot of the errors come up when you're doing, like, let's say, text generation. The syntax doesn't look good, or but like the other way might make more sense, because like images are going to be extremely high. Like you can't just do black spot whatever, like generated. Like masking is not like an ideal solution for a pixel. Like if you did it the other way, there's actually just like this thing that Meta came up with, coconut. Like coconut is it's a chain of thought latent. So what they're doing is they're just.
This always seemed more like it would make more sense to me other than you get to know what the model's thinking.
You don't get to know what the model's thinking. You may be able to decode that later. It doesn't mean like you absolutely can't, but it is harder. It's less precise. But like the great thing about it is all the probabilistic possibilities are in that chain of thought. Like let's say autoregressive. This is autoregressive. So it's just generating token. It's saying like, okay, hey, let's say at the highest level, it's a concept, like you're generating just a tiny amount of tokens that will then do a problem, solve like a math problem or something like that. It's a high level concept that it's encoded like, okay, I'm making this up, it won't be like this, but like 30%, then I need to do a sine next. 10% it should be tangent.
Oh yeah, I see it. Okay.
Yeah, like obviously it'll be like a lot of like the idea is like if you mess up, like you still have the latent reasoning. Like a lot of times you end up in a dead path if you auto-regress your way to thought that doesn't work out. Like you don't know what else you were considering in the early stages. If you keep the probabilities, you do. Like you can take the top one. You can actually like even split it down afterwards.
So that's the tree search, right?
Like a tree search. Like it basically it becomes that's what Coconut says too. It becomes a tree search because you have all the probabilities and you're just going down paths, and you don't like the path you went down. You can you backtrack and go down a different one.
That's cool.
So yours is diffusion multimodal.
But the idea will be efficient inference. So some algorithm system co-design for inference of these multimodal diffusion models.
Because the kernel also spends some extra time.
I'm not sure exactly what route it's going to take yet. One of the things I'm looking at is like task dependent or modality dependent thresholding and caching mechanisms. But I would like to take it down the quantization route as well, because like it's a £7 billion model. It's hefty. It seems like a natural way. Like basically everything I'm going to look at is a modality-aware version of something.
In general, you can try both.
I know what you mean about the cache. So KV cache, like only autoregressive are able to get that efficiency.
So block diffusion models can.
How does that work? I don't know that.
So diffusion, you have to do it across the whole sequence. Block diffusion.
You can do this.
You do it in chunks. So you can cache. You only diffuse a single block at a time. So it kind of interpolates between autoregression and diffusion. But this is kind of more common among
Sure, it makes sense. I imagine it would be kind of like chain of thought at that point. Like I'm set like diffusion like set output for the block. So I'm saying like, okay, the first block I'm going to make is not real output.
Yeah, say the first block is your prefill.
First box prefill for the prompt that I just gave it. Let's say second block after that, it's not real. It's not my output yet. I'm doing an intermediate that nobody will ever see, my reasoning tokens or whatever. I think that's what you're kind of saying, something like.
Well, so I mean, you could set it up like that. I mean, you can do this. You can do this for non-reasoning models as well, right? Like you don't have to. You don't have. It would be a nice way to hide the reasoning. You have reasoning blocks and you have actual text.
You kind of need to do it like that though, because you don't know what your output looks like. Like if you're doing output block by block, unless like it's something very structured, like I'm making this up. This won't be good, but like I'm doing chapters in a book or something. Like I know first chapter has to be 10 pages, 10,000 tokens or whatever, or right, like million tokens. So I do that.
This is one of the fundamentals. You do have more of a fix in the formatting.
Yeah, but that may work better for chain of thought than if a person asks for something completely random. Like that's not necessarily ideal, right? Like because you're doing this efficiency. You may not need more.
Yes. And then 5, and then you select the best one. I think always select one with friends. It's very similar. So, but if you are interested, I can tell you something. Yeah, that would be perfect. Sure. Okay, so I'll yes, yourself the email. Thank you. I just want to say thank you. Strange team. Thank you. Very much. My first interview, you want to listen. If it is your first time teaching, you're very good team. Yeah. Thank you. So, let me know.
Are you
going to be asking lots of questions?
questions to ask? Yeah.
Not a room. Yeah. It's like this is the harsh realities.
It's a toilet stuff.
I don't know.
What is behind you?
Signs.
People already.
I'm impressed we found it.
Have you read it?
No. I was thinking about reading it because I really liked the films. Did someone draw on the wall?
Yes, I'm very excited about it. They are zero, the most.
I would love it if there was a little recording that you could see of a person doing that and then realizing, oh god, it's just shit, let's leave.
Already set up.
Yes, I go
Thank
ahead.
you very much.
I like to claim the credit, but I wouldn't have made it to the room in reality.
Great. Thanks again for accepting our invitation.
There won't be so much mathematics in the talk, but
We have a disciplinary teams.
I used to be a theoretical physicist, but that was a long time ago.
So, are you connected with your laptop?
Yes.
Have you tried also to connect to Teams?
No.
Okay.
I just finished it.
I can probably do it. There is a Teams link, right?
Really?
Because I really like the movie.
Yeah.
And
Have you
it's
seen the modern one as well?
just one more.
This one, right?
But it's like
The one who wants to start
he
the
does a
meeting.
fantastic job.
Yeah.
The world is very rich. There's a lot going on.
Should I use my
I just feel like the characters are quite two-dimensional. And then there's a lot of stuff where,
I can do a room audio
like,
apparently.
as a character who
Is there a two-room audio? No. It says audio subject.
Yeah.
And it's
It's
like-
not real. I mean, it's in
Yeah,
this
especially if it happens more than once, you're kind of like, well,
yeah,
now
yeah.
it's just a
The first time it's a plot twist. The
Yeah, it's
second
like a-
time it's like,
and the third time you're like, I'm bored of this.
yeah.
Yeah. What, the June book?
The first book's good, but some rubbish.
I didn't like it that much. Like it was good, but I felt like he did.
No, usually does. I mean,
His
now
characters
that's
weren't
true.
very.
Yes, and I see it.
And
I do this.
no, but I like my.
I mean, like, should I unmute myself?
That have really good characters as well as world building. Because it's like you can have good world building, good characters, and good plot, and like not. You can only have 2 of the 3.
I feel like
Noise suppression.
I don't know how complex is Han Solo.
Not very.
Just a guy, really.
He's just a guy.
smuggler.
Yeah.
There's no character in Star Wars. None. Zero. Nobody has a complex character in Star Wars.
Yes.
Okay, so
The rings.
No, that's the background. This is my initial stuff. Yeah, I was going to start for an equal, it's very
Never really go.
metaphor about trees and all. I don't know.
You read any
what
Brandon
it is.
Sanderson?
Probably the default background of Symphoria.
Yeah, trilogy.
yeah, I enjoyed them. Yeah. I think my point of reference was something like is Game of Thrones, where
None of them have characters.
in Game of
Each
Thrones,
shag dies and then repeat in different orders.
Yeah.
I like
They go to the feast, they shag something, and then they die, and then
I
they swap
like
out.
politics in Game of Thrones, and there was not really politics in Dune. It's just like there is politics in the background, and we're just going to ignore that because we've got the Messiah and he's going to destroy it all, and it's fine.
That's why I was like,
Don't worry about it. Like, you don't have to do anything interesting politically because you're the Messiah.
But the political thing was kind of like just established, and it was kind of like this is what it is.
Yeah, I think he builds into it in the later books, maybe.
Yeah,
after.
but then also does some great things from what I've heard.
What's the third film going to be? Messiah? The book Messiah? Is that
I think, yeah,
It's like children. There's like 10 books.
I think it's the first book turned into the first 2 movies, and then the second book.
twists.
There is some good complexity. So, like, to Paul, he's a complex character. He changes.
What's interesting about it is the twist happened. And there's no, they had to kind of put in some jeopardy, and there's no jeopardy. Once they've been knocked over, then from that point on, it's a weird. The structure of the narrative is quite unusual.
I mean, the book series, if the politics in that book gets to be interesting, I'll. It's like an interesting set of
on paper I have.
It does seem like it's quite political.
So that's
a trilogy, but only the second one is out. So there's the second. So the next one will be a while.
I literally.
I'm really enjoying it so far.
Have you read June?
This person knows.
She works in publishing.
This is I really enjoying it so far. It's kind of like a post-cataclysm world.
Exactly.
It's a big cataclysmic event.